Okay, here we are at video 8, the last one in the series from my notebook when I started to study general relativity. This is the Riemann curvature tensor. It looks like this, R in honor of Bernard Riemann. It's a 4-index tensor, and why you want it is that if this tensor is equal to 0, then the manifold you're studying, the surface you're studying is flat. If it's not 0, then it's curved. So it's a very good way to tell if something is curved or flat intrinsically, which means what? We're walking around on it. We're not looking at it from above, we're walking around on it. All right, so let's look at this beast. I offer it here without a derivation. I'm going to leave a video link in the description. I did a video on deriving this, but it is very long, it's very tedious, a lot of advanced math in it, the covariant derivative, which we did not cover, but I welcome you to watch it because it's a lot of fun and you might learn something. So, like I said, this is a 4-index tensor. So we got 4 for the free indexes, right? So we got the derivatives of Christoffel symbols with respect to coordinates here and here. We got the product of Christoffel symbols. And you notice here you got a tau in the upper and a tau in the lower. These are summation indexes, okay? So what we're going to do is only in 2 dimensions. So we're going to, oh, there's that. We would need a 16 of these things. And since we have 2 dimensions, there would be 4 of these terms. There'd be one of these, and 4 of these for each one of these times the 16 we would need to do. Turns out there are only 4 of them are non-zero. I've done this before, so I don't want to do the 0 ones because it's really it's a lot of work just to get disappointed at the end. The climax is awful. You get a 0 and you're like, oh, I did all that. So we're just going to do the ones that are non-zero. So here's the things that we need. These are the non-zero Christoffel symbols that we found. There's only 3 of them, okay? Here's our generalized, the formula, and we're going to start with R, the theta, phi, theta, phi. Okay, so look at this. Here's your sigma is theta. So you go through this equation, you put the theta every time you find a sigma. Okay, and when you get down here, alpha is your phi, beta is your theta, and gamma is your phi. And now look over here, you see you got 1, 2, 3, 4 terms. That's because these are the summation indexes. So in the first case, tau is theta, 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 theta. The second case, it's phi, 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 phi. So you put all of that in, then you go back and look and see if you got any of these to start with, right? Okay, so we had this one was non-zero, which is this. And the very last one, this one here, is non-zero, which is this is the cotangent to theta, and this is that. Okay, so we need to take the derivative of this first. And this, I used the product rule here, right? First times derivative of the second plus the second times derivative of the first with respect to theta. I changed the cotangent to theta to cosine over sine because that's what it is. And that's obvious why I want to do that, right? All right. So the the derivative of cosine is minus sine. It wipes out that negative. The derivative of sine is cosine, so that's going to give us a cosine squared. This sine wipes out that sine. We got a cosine squared. And these 2 cosines are gone. They cancel, and we got sine squared theta. And I'm going to write it here in red so I can go back and easily find it. Now, there is a unique property of the Riemann tensor, which is that it is asymmetric about its last 2 indices. So I've got ABC down here. If I change that to ACB, I get the negative. So this is the negative of that. So when you find one of these rascals, just swap these 2 indices and you have another one, which is the negative of that one. You got it? This is a unique property of this. All right, so let's go find the other 2. All right, this is what we need. We write it down. Here's our generalized the formula again. And this time it is phi theta theta phi. All right, and let's see what ones hit. I see it would be uh, theta of phi. It would be this one, right? So we got the partial of this with respect to theta, and then it is these two, the cotangents. Okay, so so I'm going to write the cotangent as the cosine over sine. This is just cotangent to squared. Now I'm going to bring this sine up like this to be a -1. So cosine theta sine minus 1 theta is the same as that, right? And the reason I can do that is so I can use the product rule. It just makes it easier in my mind, right? So we got the first times derivative of the second. So I bring out my -1 from here. That makes this, I subtract a 1, it makes it a -2. Then I'd take the derivative of what's inside, which is cosine. The sine of the derivative of sine is cosine. All right. Then it's the second times derivative of the first, which is a negative sine. Then I got my cotangent, the squared. All right. So let's see what we're going to have here. We're going to have a cosine squared right there. We got a negative sine. We got our sine squared. I'm going to put it back on the bottom. And minus this wipes out that and leaves a -1, right? And then we got our cotangent, the squared here. So we wind up with minus cotangent squared theta minus 1 plus. So these two wipe out. That is the same thing as cotangent squared. Boy, I probably didn't explain that very well. Okay. So we get a -1, right? And once again, we do our trick. We swap these two indices and we get a +1. Excuse me. All right. So we've got 4 hits non-zero of the Riemann curvature tensor. Now what do? We want to find the Ricci tensor, which is what was used in Einstein field equations, right? So R mu nu is the Ricci, the tensor. R is the Ricci scalar. G mu nu is the metric tensor. That's what we've been doing the whole time. That's a bunch of constants. And the last one, T mu nu, is the energy momentum, the tensor. Okay, so we want to find the Ricci tensor. So how do we get from here to here? We got a 4-index tensor and we want a 2-index tensor. Well, it's called tensor contraction, okay? And okay, to do our tensor contraction, what we're going to do is take a 4-index the tensor, change 2 of these upper and lower indexes to the same letter, and that leaves a 2-index tensor because that makes this a summation index, right? Since we only got 2 dimensions, then we only have to be concerned about theta, theta, and phi, phi. Then we do all the permutations of mu and nu, which means if in 2 dimensions, there will be 4 of these, right? So here is our non-zero components of the Riemann, the tensor, right? So let's do the first one is r theta theta. So mu and nu are both thetas, and they're our free indexes. So we have to put them here, 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 anywhere you see a mu and a nu. Then our summation index is theta, theta, and phi, phi. We got one of these. This one's 0. We don't have one of those. And this one's 1. So we got 1 hit. These are all 0. These are all 0. And this one has a non-zero, which is this. This is 0. But this is sine squared theta. All right. So we got 2 non-zero components of the Ricci, the tensor. Now what do? We're going to do the same thing with the Ricci tensor. If we contract the Ricci tensor, which is a rank 2, with another rank 2 tensor, which you recognize as a contravariant metric tensor, inverse metric tensor, you get a rank 0 tensor, which is a scalar. All right. So since both of these are now summation indexes, it makes this really easy. You just do all the permutations of mu and nu, right? The theta, 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 phi, phi, theta, phi, phi. And so we have to go back and get our 2 non-zero components of the inverse metric tensor, We got our two non-zero components of the Ricci tensor. We fill all of this in, and the sine squared theta cancels out. We got 1 over a squared, 1 over a squared. We got 2 1 over a squared, so it's 2 over a squared. So the Ricci scalar for the surface of a sphere is 2 over a squared. Remember, a was the radius, a constant or the radius. Okay, wasn't that fun? Thanks for watching. I'll see you later.